There we go. All right. Hello and good afternoon. Welcome to the end of week 2, which is crazy. After today, and it's the beginning of the end right now. Sorry while I rearrange my stuff. Today's the beginning of the end of week 2. Because let's be real, we've got an hour and a half lecture, and then we have 3 hours of office hours. So it'll be a longer day today. So we have plenty of the end left to enjoy. Today we are going to be finishing off chapter 4. Surprisingly, we haven't fallen behind in our tentative lecture schedule, which is good. So yeah, it's a couple things to keep in mind. One is okay. I haven't yet. I know there have been questions about typos about the prereq exam. I'm going to be looking at that over this weekend, and I will post an announcement when that goes live. In addition, I have not yet graded the free response questions in that first lab. And again, I'll post when those have been updated, so you're not left wondering, like looking at the number, thinking, is it the same? Is it different? Has he graded it? Has he not? I will let you know, so you will know. And then another thing to keep in mind is that we have. Hang on. I'll just refresh this page. There we go. We actually have our exam 1 is looming on the horizon. Technically, it's the second exam, right? We've already taken a test in this class, the prereq, but this will be our first one based on course content, based on chemistry. And here we go. So exam 1 is still a week away-ish. It will open, and all this information is in the syllabus, but I just kind of wanted to put it in everyone's consciousness. It'll open on next Friday, so a week from tomorrow, and it closes that Sunday night. So it opens at 12 a.m. Friday morning and closes 11:59 p.m. Sunday night. And during that time, I will not be available to answer questions. So when the exam is open, it's going to be radio silence from me. So you'll have all of next week, 2 office hours to get the questions answered that you need, and then you'll be on your own. Parthana, great question. Exam 1 will cover chapters 1 through chapter 4. All right, we're currently in chapter 4 right now. So I think question. Actually, wait, hang on. Let me check. Okay, hang on. I'm actually not ready to commit to that yet. There will most likely be some chapter 5. I don't know yet because I haven't written the exam. I'm going to be sitting down this weekend and taking a good hard look at how much material there is. I'm going to be writing a decent chunk of the exam. So I will have more information next week. So there's more info to come. One thing to be aware of is I will also be, when I say more information, I'll be given, yes, exactly, Esther. That is actually literally the thing I was going to say next. I will be telling you, once I have the exam more written down, I'll be telling you how much each chapter is represented. So I'll be like, oh, exam 1, 13% of the problems are from chapter 2, 14% are from chapter 3. I'll tell you exactly how much, so you know what to allocate time to. I can't give you exact percentages right now because I don't have the test written. But here's what I would recommend, because I realize this is a primetime study. This weekend is primetime study time for the exam, since you'll be taking it sometime next weekend. And so what I can tell you right now is the focus for exam 1. So if you're like, what's the most important stuff to look at? It'll primarily be chapter 2, 3, and 4. That's what I would zero in on. There could be a little chapter 1 and chapter 5. So this is a possibility, but it's not going to be the focus of the exam. So this weekend I would definitely hit chapters 2 through 4 hard, because that will be represented heavily on the exam. Okay, Brianna, will you be given... the exam will be timed, but the amount of time you'll have to take it will depend upon how many problems there are and what types of problems there are. So I will be determining the length of the exam once I know how many problems and how difficult those problems are. So it'll definitely be a timed exam, but you will have this window in which to take it, Friday to Sunday, at any point during that time. So you can choose to take it Sunday evening, and that'll give you Friday, Saturday, and then most of Sunday to study and prepare for it. Or if you like to get things out of the way early, you can just take it Friday and enjoy your weekend. So anyways, you'll have the choice of when to start it, but it will definitely be timed. And again, more info coming next week on how much time you'll have. All right. So I think that's it. Do you guys have any other questions about the test before we move on? Yeah. Totally timed. It'll also be the questions will be randomly generated. So, for example, if there's a ion question where it's like, oh, what's the ionic charge of this ion? What charge would it develop? You will all get different questions, because what I do is I don't write what's the ionic charge for that fluorine gets. I write a bank of problems. So when you log on to take the exam, it pulls out of the bank at random unique problems from all the types of problems. So everybody ends up taking a unique test. So if you're thinking like, oh, well, I'll just have my friend take it and then they'll tell me what the answers are, you'll be seeing different problems. So it won't be as helpful as it may otherwise be. Let's see, will the test similar to the homework assignments? Esther, that is a great question. I'm not exactly sure, because I haven't written the test yet, so I don't know how similar or dissimilar it'll be. What I can say is the homework assignments, I write those with, I write those problems as kind of easy to mid-range difficulty. I don't really put like really hard problems on the homework, because I want the homework there to reward you guys. I don't want it to be this like gnarly thing. I want it to be fairly accessible so you can score those points. The exam will have some easy problems, some medium problems, but then also some very hard problems as well. So the homework will give you a taste of what easy and middle tastes like, but it's not really, I don't put the really gnarly problems on the homework. How much time would you say are allocated per question? Carenza, I'm not sure at this moment in time, just because I haven't written it. I'll have much more specific information coming out into Monday. Any questions from the labs? Anything is totally fair game, Jen. But what I would say, anything's fair game because that any material that's related to the chapters that the exam covers. So anything that's related to chapter 2 or chapter 3 or chapter 4. But for example, one of your labs was that manganese catalyzed decomposition of hydrogen peroxide. That wouldn't be on the exam because we haven't talked about reactions yet. So it's going to focus on the material we've covered in lecture. Let's see, is there a specific resource practice problems we could use, practice for harder questions? I mean, honestly, Carenza, that is an excellent question. I would, there's all the questions, homework problems in the back of the book, which are great, and I assign those for practice. So if you're looking for practice, hit up those. But then if you're out of problems and you're I want more practice, use the internet. Google chemistry, then do the topic type worksheet. So Google chemistry naming ions worksheet, and you'll have a ton. Or chemistry electron configuration worksheet, and the internet will burst forth with a bunch of worksheets from a bunch of different colleges that'll give you tons of reps. So your only limit is how much you're willing to type into Google. There's tons of resources out there at your fingertips. Okay. All right. I'm going to shift gears now. We've been talking about the exam for 10 minutes. We definitely have some lecture material to cover, so let's go ahead and dive in there. The reason why I brought it up now is just to kind of put it on everyone's radar. Again, keep an eye on the syllabus to stay up on when your assignments and stuff are coming due, but this weekend will be primetime study because next weekend is when you take the exam. Again, at your leisure within that window. Okay, so we all know the exam is coming, that our doom is nigh. Let's learn a little bit more about what our doom includes, because all the stuff that I'm covering today will have a decent representation on the exam. So we've been talking about ions, which has been awesome. We've been talking about where they come from, right? Why ions form. We know how to look at a main group element and determine what kind of ionic charge it'll develop, right? And now, what we're going to do now is I want to take a moment to cover nomenclature, all right? I want to talk about naming ionic compounds. All right, naming ionic compounds. Or compounds. So naming ionic compounds is fairly straightforward, all right? So the way you name an ionic compound is an ionic compound, an ionic compound's name is the cation name, followed by the anion name, but then you take the end of that anion name, chop it off, and add "ide." All right? Cation name plus anion name with an "ide" there at the end. That is how you name every ionic compound. Let me show you what I mean. All right? NaCl, if I were to ask you to name this ionic compound, well, what's the name of our cation? Cation in this case is, I almost wrote nodium, sodium, The anion name is chlorine, but you chop off that end and add ide. So this ion's name is sodium chloride, right? Let's name another compound, ionic compound. All right, here, our cation's name is magnesium. Oh, forgot the whole point of color coding things is to color code them, right? This is magnesium. Our anion is bromine, but again, you chop off that end and add an ide, bromide. All right, let's do a third example. Al2O3. All right, here our cation is aluminum. All right, and our anion is oxygen. But here, with our anion, we chop off the end and add ide. So this would be aluminum oxide, magnesium bromide, sodium chloride. All right? So that is how you take the chemical formula of an ionic compound and turn it into and turn it into a name. Now let's do this process in reverse. All right, let's take a name and write the chemical formula for it. Before we do, there's one thing you have to be aware of. So I have one. Susan, that is correct. With ionic compounds, you do not have to include the subscripts in the name. It's just sodium chloride. It's just magnesium bromide. You don't have to say like add a di or tri or whatever. It's just anion name plus cation name plus anion name with an ide. One thing to keep in mind as we're about to do the reverse process is remember this one thing. Ionic compounds are always net neutral. We've talked about net neutral a little bit yesterday, but what this means is that the total negative plus the total positive charges will always add to zero. All right, the negative charges of all your anions plus the positive charges of all your cations will always add to zero, and this is what you'll need to take our names and determine the chemical formula for each. So for example, let's write the chemical formula for potassium bromide. All right, and to do this, we're going to need to grab our periodic table. Here, hang on one second. Hey babe, I can totally come through. Alrighty. Okay. Sorry for the sound leak. If you could hear low level voices moaning, bro. I'm pretty sure people are having fun on a Switch right now. Okay, or maybe not having fun, as the case may be. Okay, potassium bromide. So We got to locate our cation. Oops. Potassium, which is right here. Its nearest noble gas is argon with 18. Potassium has 19, so potassium as a cation will have a charge of positive 1. When we locate bromine, 35, it's 1 away from krypton, it's 36. So bromine as an anion will have a charge of negative 1. Now, because the charges match, right, we have a positive 1 and a negative 1, that means potassium bromide will combine in a 1-to-1 ratio. So potassium bromide is just KBr. And that is our chemical formula. All right? Let's do another example. Let's do sodium sulfide. All right, so sodium is number 11. Its nearest noble gas is 10. Right, so it needs to lose 1 electron. It'll pick up a charge of positive 1. Sulfide, right here, 16, is 2 away from argon, who has 18. So sulfide is going to pick up a charge of negative 2. Okay, well, Peyton, I'm so glad that you don't. I also it could be in these headphones that I can I might be hyper aware of the trace noise pollution, but I'm glad it's not eking through. Okay. So sodium has a positive 1, sulfide has a negative 2. That means to be net neutral, we need 2 sodium ions, to cancel, to balance the negative 2 on sulfide. So sodium sulfide has a chemical formula of Na2S. Okay, when naming ionic compounds, how do we identify which elements in the compound are cationic and anionic? Cationic is positive, anionic is negative, but it seems like we just write them in the order it's presented. Carenza, great question. So for cationic and anionic names, so for when you name ionic compounds, it's always the order is cation first, anion second. Always. So you always list the cation first and then the anion second. Now, when we write chemical formulas, we also write cation first, anion second. So it's presented in this format, and you also name it in this format. So one kind of mirrors the other. All right. Let's do another example. Let's do calcium nitride. All right, calcium. It's number 20. It wants to be like its nearest noble gas, argon, which is 18. So calcium will lose 2 electrons, picking up a charge of positive 2. Nitride, our anion, is nitrogen. Nitrogen wants to be like neon, which is 10. Nitride has, okay, awesome. Nitride has 7, so nitride needs to gain 3 electrons, so it will have a charge of negative 3. Now, here, you'll notice that we've got a little bit of a problem. All right? here we have two charges that do not go into each other evenly. Any of the subscripts? Jen, great question. The subscripts in these formulas are always positive. Okay, so we've got a little bit of a problem here. We've got a positive 2 and a negative 3. 2 and 3 don't go into each other evenly, all right? So when you have the situation where your positive and negative charges do not go into each other an even number of times, there's a quick and dirty trick that you can use to get the correct chemical formula. And it works every time when your charges don't go into each other evenly. For your cation, what you're going to do is take your anionic charge and make that your cation's subscript. Then for your anion, take your cationic charge and make this your anion subscript. This is the chemical formula for calcium nitride. All right? And here's why this works. All right? Calcium, as we know, has a charge of positive 2. Nitride has a charge of negative 3. When you multiply your positive 2 by 3 and your negative 3 by 2 and add them, what happens? You end up with positive 6 and negative 6, and these sum to 0, and we know that every ionic compound is net neutral. The total positive and the total negative adds to 0. Yes, Prathana, it totally is. Totally. All right, so that's what you do when you have a positive and negative charge that don't go into each other evenly. Just swap them for your anions and cations, and that'll drop you right into your answer. All right? Now, I want to draw our attention to something. So I've been dodging something this entire chapter. This whole chapter, we've been looking at ionic compounds and ions and whatnot. We've only been looking at main group elements, all right? But now I want to draw our attention to the transition metals. All right. So here's the question. Why am I dodging the D block? All right. Why am I dodging the D block? Why am I not interacting with the transition metals? Well, it turns out that the transition metals are a little more complicated than main group elements. Main group elements are nice because they follow very rigid rules and they always have the same charges, and so they're easy because they're predictable. Transition metals are not. All right. You can look at the periodic table at any main group element and know what charge it's going to develop when it becomes an ion. We're not so fortunate with the transition metals, all right? So transition metals, I should say it like this. You cannot predict the charge of D block elements you can't predict the charge of D block elements with the periodic table. All right. And that it's because they're more complicated. They're not as cut and dry as the main group. And you may be going, oh no, that sounds harder. But actually, in practice, it's easier. You cannot predict. You can't predict the charge. So you have to be told. It actually makes your life a little bit easier. For example, I could ask you to write the chemical formula for lithium fluoride. All right, I could ask you to write the chemical formula for lithium fluoride, and you could, because you could look at the periodic table, see that lithium is going to lose one electron to be like helium. So it's going to pick up a charge of positive 1. And you could look at fluoride and see that fluoride is going to gain an electron to be like neon. So it'll have a charge of negative 1. And so lithium fluoride will have a chemical equation of LiF. You can do that from the periodic table. I cannot write the name let's see. I can't write copper chloride and expect you to figure out the chemical formula because, well, we can look at chloride and go, okay, chloride's going to gain 1 electron. We know from the periodic table it'll have a charge of negative 1. But when you look at copper, Cu, it's in the D block. It's a transition metal. So you have no way of knowing what charge this thing has. I can't ask you, write the chemical formula for copper chloride, so I have to tell you what the charge is. And I tell you what the charge is by putting it in Roman numerals in parentheses next to the transition metal. So I can't ask you, write the chemical formula for copper chloride, but I can ask you to write the chemical formula for copper 1 chloride. Now, because I've told you, I've explicitly stated that charge, you know that copper 1 chloride has a charge of positive 1, and so it will have a chemical formula of, let's see, CuCl. All right? And this is a different compound than copper 2 chloride. All right, copper 2 chloride. In copper 2 chloride, you still have the chloride anion, charge negative 1, but now your copper cation in this compound, it has a charge of positive 2. So now we need 2 chlorides to balance with our copper. So copper 2 chloride has a chemical formula of CuCl2. All right, when it comes to main group elements, all you need is the periodic table. When it comes to transition metals, I have to explicitly state the charge of your transition metal by placing it in Roman numerals next to the compound. Cool? Okay. Now, this is a little bit easier when you are taking a name and using it to find you're taking a name and using it to find a chemical formula. It's a little bit harder, it's a little more challenging when you're using the formula to name an ionic compound? At Susan, you totally could. You just have to be careful with swapping when it comes to whenever it's not, you don't have a charge of 1, whether it's positive or negative 1. So like if you had like 2 and 4, you couldn't swap those two because 2 goes into 4 twice. So you need 2 of the plus 2 thing and 1 of the negative 4 thing, etc. But as long as your charge is 1, either positive or negative, you can totally do the swap thing. Okay, let's take a few. Let's name a few ionic compounds. All right. For example, let's name. And let's name. All right. When you're naming ionic compounds, the first thing you want to do is identify where on the periodic table they fall. All right, chloride is right here. It's 1 away from argon, right? So we know it's going to pick up. Because, okay. Carenza, that is an excellent question. So Carenza just asked, why can't we use the periodic table to determine the charge of transition metals? And the answer is the reason why we can't is this: transition metals do not follow any repeatable pattern. For the charges they adopt in nature. And a single transition metal can have different charges in different compounds. So the answer to your question is there's no repeatable pattern. There's no way of looking at the periodic table and going, oh, it's right here, so therefore it has this charge. And the same metal can have different charges in different compounds. The main group elements are awesome because they always have the same charge. Sodium is always +1. Iron could be +1, +2, +3, +6, depending upon the compound it's in. So not only is there no repeating pattern, but often transition metals can take on more than one charge, depending upon the compound. Yes, yeah, totally. It absolutely is why they're called transition metals. They are very, very fluid. Very fluid. Easily the most flexible group of compounds, or not compounds, elements on the periodic table. Their reactivity is diverse, their bonding structures are diverse, they're amazing because they're complicated, and they're complicated so it makes them a little more challenging to deal with. Alright, so let's name these. You'll notice that, so we've identified chloride, right? We know that it's going to pick up a charge of -1, but our metal in both of these is the same. It's nickel, which falls right here on the periodic table. All right, now, here's the thing. If this were a normal ionic compound, by saying normal, if we were dealing with main group elements, we could just call this nickel chloride. Here's the problem. The compound right underneath it, by the same method, would take the same name. right? And these are two different compounds because we've got different numbers of chloride ions in each one. NiCl2 is a different compound than NiCl3, so they can't have the same name. The way we differentiate them is we have to add a parentheses with the charge of the transition metal in a Roman numeral. And what that means is we need to determine what that charge is. All right? So here's how you do it. All right, you need to set up a formula. You know that the charge on nickel plus 2 times the charge on chlorine has to equal to the total charge on this species, which is 0. All right? And we know the charge for chloride, right? Cl minus has a charge of -1. So that means for the first compound, the charge on nickel plus 2 times the charge for chlorine, right, which is a -1, is equal to our total charge, which is 0. So if nickel, the charge on nickel minus 2 is 0, that must mean that the charge on nickel is plus 2. All right, and that is what we put in our parentheses. This is nickel 2 chloride is the name of that first compound. Let's do the same thing. Let's use the same method to find, to name our second compound here. So we have the, we know that the charge of our nickel cation plus 3 times the charge of chlorine, or chloride anions, will equal 0. We don't know the charge for nickel, but we do know that each chloride ion in this compound has a charge of -1. And these will all add to 0. So we have nickel, the charge on nickel, minus 3 equals 0. So that means the charge on nickel in this compound is a positive 3. So we need to add the Roman numeral 3. So the name of our first compound is nickel 2 chloride. The name of the second compound is nickel 3 chloride. All right, and it's important to note that these Roman numerals are the cationic charge. All right, they're the cationic charge. They are not the number of nickels, because if you look in each compound, there's only one nickel atom, but the nickel atom in the first one has a charge of positive 2. The nickel atom in the second one has a charge of positive 3. Cool? All right. So that is how you handle transition metals. Again, you're going to need to get a lot of repetition in. There's a lot of additional homework problems assigned covering this. We're going to stay talking about ions, but we're going to shift gears just a little bit because there's one last thing we need to cover before we have naming ionic compounds done, and those are the polyatomic ions. All right, polyatomic ions. These are, so all the ions that we've looked at up to this moment in time have been single atoms. There's only one atom, one nucleus present, and it gets positively charged or negatively charged. Polyatomic ions are ions that are made up of multiple atoms, but as a group, those atoms all have a charge, all right? And there's a list. I'm going to write them out for you right here. NO3 has a -1 charge, is called Nitrate. Let's see. Can we just have this descriptive attention between okay, so we've got nitrate, we have NH4 has a positive 1 charge. This is ammonium. All right. HSO4 has a negative 1 charge. This is called bisulfate. It's also called hydrogen sulfate. It can go by either. SO4 with a negative 2 charge is sulfate. All right, now we have the phosphates. PO4 has a negative 3 charge. And this is this is phosphate. HPO4 with a negative 2 charge is hydrogen phosphate. And then H2PO4 with a negative 1 charge is dihydrogen phosphate. CO3 with a negative 2 charge is carbonate. HCO3 with a negative 1 charge is bicarbonate. Or hydrogen carbonate, it goes by either. Let's see, what do we have? We've got CN is a fan favorite. This is cyanide. H3O plus is hydronium. And OH minus is hydroxide. All right, now the reason why I took the time to write these out is I highly recommend that you commit these to memory. Again, in a regular class, in-person class, I require you to memorize them, but because you're taking all your exams at home, you can always look them up. But what I will say is if you have these memorized, you're going to use them so frequently that if you're having to search them, if you're having to Google them every time, you're going to be losing time on the exam, and that's going to put you behind. So if you don't have these memorized, you can still look them up, but you may lose points that if you had them memorized and you could just spit them out, you'll probably score more because time will be less of an issue for you. So I highly recommend that you memorize, but it's totally your call. Now, the reason why we're mentioning them here, so I wanted to get them all on the board. I'm going to have to clear the board now. We're going to start naming compounds using polyatomic ions. All right. So, for example, we're going to start naming and writing chemical formula. So if I give you the formula, or sorry, the name, sodium sulfate, sodium, cationic charge of +1. Sulfate is a polyatomic ion. You just have to know it's SO4 with a -2 charge. And since we need 2 positive ones to balance with our -2, so sodium sulfate will be Na2SO4. All right. Let's do iridium 3 cyanide. Now, iridium is a transition metal, but you don't have to stress over the charge because the charge is a +3. All right. Now, cyanide is a polyatomic ion, Cn with a -1. Now here, if you write IRCN3, this is incorrect, all right? Because this compound has 1 iridium, 1 carbon, and 3 nitrogen. Anytime you have more than 1 polyatomic ion, you have to put it inside a parentheses with a subscript on the outside, all right? This is the only way to write formulas with more than 1. Polyatomic ion. All right, you'll notice that sulfate doesn't have a parentheses because there's only 1 in the previous compound. But if you have more than 1, you got to slap it inside a parentheses. All right. Let's do one more example. How about ammonium carbonate? Or no, let's do ammonium phosphate. All right, here we have 2 polyatomic ions. One is ammonium, NH4 with a +1. Our second one is phosphate, PO4 with a -3. And here, we're going to need 3 ammoniums to balance with our phosphate's charge. So we put ammonium, NH4, inside a parentheses, give that a subscript of 3, followed by PO4, and that is ammonium phosphate. Iridium cyanide, and sodium sulfate. You'd use these polyatomic ions with naming and writing chemical formula exactly the same as you do any other ion, with the exception that when you have multiples, you throw them in parentheses. All right. Now, I highly recommend you work on do all the naming homework. It's super clutch. It's not going to go away. You're going to be using it for the rest of the semester. So this is something you want to put in the time for. All right. Now, with our last bit of lecture today, I want to talk about. So we've been talking about all sorts of ionic stuff, right? All sorts of ionic stuff. We've talked about how to. Oh, I'm sorry, Jen. It's the pain of summer. Things move very, very quickly. Things move very quickly, but if you're dedicated, you can do it. And I believe in you. Okay, with our last few minutes of lecture here, we've been talking all about ions, right? We've talked about what their charges are. No. This is everybody. We are all in this storm, and it's it's hard for everyone, and you feel alone until you vocalize it, and then you realize that you're there with a bunch of people. Yes, Carenza, there are tons of these to practice in the book. I assigned so many practice homeworks for just naming. Yes, totally. We can totally hit tons of review in office hours, Jen. Totally. We've got one last subject to hit now, but we can do tons of naming practice when it circles around at 3. All right. So we've been talking about the charges ion forms, why they take on the charges that they take on, right? But the one thing that we haven't talked about when it comes to ionic compounds is how they form. All right, and that is the last thing that we're going to cover in this chapter, how ionic compounds actually come about. How does sodium get stuck with chloride? How does magnesium get stuck with bromide? Before we do, we need to talk about something called a Lewis dot structure. All right, a Lewis dot structure is just another way to depict the number of valence electrons an atom will have. All right. So if you look at, for example, if you look at, well, for example, lithium. All right. Lithium has a electron configuration with helium, right? That's its noble gas. And then it's 2s1. In a Lewis dot structure, you take that one electron, and the way you depict electrons in a Lewis dot structure is with dots. So you take the elemental symbol, and for every valence electron, you put a dot next to it. So the Lewis dot structure for lithium would be just Li dot. All right. What about beryllium? Well, if you look at the electron configuration, it's 2s2. So beryllium, because it has 2 valence electrons, would have 2 dots. All right. Let's jump ahead a little bit. Let's look at carbon. Carbon has an electron configuration 2s2. Oh, sorry. 2s2, 2p2. Now carbon has a total of 4 valence electrons. So in the Lewis dot structure, you go 1, 2, 3, 4. All right. What happens if we have more than 4? Right. Like let's look at oxygen. Oxygen's electron configuration 2s2, 2p4. So oxygen will have a total. I'm just going to scoot it over a little bit. Of 1, 2, 3, 4, 5, 6 valence electrons. So you go 1, 2, 3, 4, 5, and 6. All right. With the Lewis dot structure, you kind of look. There's 4 sides of each element, and you just kind of circle around like I just did. If you look all the way over at neon, 2s2, 2p6. Neon, we have 8 total valence electrons. So the Lewis dot structure for neon is 1, 2, 3, 4, 5, 6, 7, 8. All right. Number of valence electrons equal the number of dots. Now, if you're asking yourself, do I need to write the electron configuration every time I draw a Lewis dot structure? The answer is no. Here's the beautiful thing. If you look at the columns of the main group that it falls in, that tells you how many dots in the structure. Everything in the first column of the main group has 1 dot. Everything in the second has 2, 3, 4, 5, 6, 7, 8. So you don't have to write out an electron configuration. You just look at where it falls in the periodic table. I just wanted to show you the correlation between the electron configuration and the Lewis dot structure at the beginning. But from here on out, just find it on the periodic table. For example, if you had to do like sulfur, you just box in sulfur, right? And then you go, oh, it's in the 6th column, so I can just write sulfur. It has 1, 2, 3, 4, 5, 6. That's my Lewis dot structure. It's that fast. Let's see. Yes, totally, Brianna. That's exactly you anticipated where I was going. So well stinking done. Okay, Susan. So here's the thing with Lewis dot structures. It doesn't matter where the dots fall. You could totally write the Lewis dot structure for oxygen like so. You could write oxygen, oops, hang on. You could totally do it like this. Just as valid. It doesn't matter where the dots fall, as long as the number is correct, as long as you have 6 total, then it doesn't matter where your pairs are and where your unpairs are. Does that make sense? So that the two don't have to be on top to the right. You could even do it like this if you wanted to. All of these are equally valid because they have the correct valence electron count. All right, now, why are we talking about Lewis dot structures? We're talking about Lewis dot structures because Lewis theory allows us to get our first real glimpse as to the how compounds form. Jen, great question. We don't. So what we're talking about right now is something called Lewis theory. And Lewis theory is a very powerful tool that can explain a lot of the bonding we see in nature and in compounds in nature, but it only works for main group elements. It does not explain the structure and reactivity of the transition metals. So Lewis theory is great, but it's for main group kids only. The transition metals can't sit with us at this moment in time. Or maybe we can't sit with them. I think that's the way it is because they're cooler, in my opinion. All right, so let's look at, how does sodium chloride even form? All right, well, let's look at the Lewis dot structure of our cation and our anion. Now, sodium has a Lewis dot structure with just 1 electron, all right? And chlorine has 7. All right? So sodium has 1 dot, chlorine has 7. Now, we know that chlorine is 1 away, right, from having the same number of electrons as argon. It's 1 away from having that noble gas configuration, which is super stable. Sodium is also 1 electron away from its nearest noble gas, but it wants to lose 1, right? It wants to lose its 11th electron to become like neon. So what happens when sodium meets chlorine is chlorine's like, dude, I want that electron, and sodium's like, I don't even want this thing. And what happens is chlorine punks sodium for its electron, but don't feel bad for sodium, it's into it. And after the reaction is over, you have sodium at its noble gas configuration, and you have chlorine at its noble gas configuration, except sodium has lost an electron, so it is now positively charged, and chlorine is now chloride. It has that electron it took from sodium, and now it is negatively charged. And these opposite charges, the positive and negative, attract each other, and that attraction between the positive cation and the negative anion is what we call the ionic bond. All right, it is that attraction between positive cation and negative anion. All right, so that's how this compound forms. You've got a sodium atom, a chlorine atom, but when they get close to each other, chlorine's like, dude, I want that electron. Sodium's like, I'm not going to eat this. Help yourself. Sodium becomes positive, chloride becomes negative. They're both happy, they're both stable with their noble gas configurations, but then they stick together because of that attraction between the now positive and negative charges. All right, let's look at another ionic compound. Let's look at how magnesium bromide forms. All right, what's going to happen when magnesium meets bromide? Well, magnesium has 2 valence electrons, all right, and bromine has 7. All right, so very similar thing's going to happen as we saw with sodium and chloride. Magnesium's looking to get rid of electrons. Bromine's looking to take electrons. So bromine will grab an electron from magnesium, which is great. But there's a problem. After bromine takes one of magnesium's electrons, it now has satisfied the octet rule. It has a noble gas configuration and a newfound negative charge. Now magnesium is left with a positive charge, but there's a problem. Magnesium still has 1 electron that it wants to get rid of. But bromine, now bromide, isn't going to take more than 1. It only needs 1 more to get that stable noble gas configuration. It's done. So bromine satisfied, magnesium isn't. Magnesium is going to keep searching until it finds a second bromine. Bromine atoms, as we've already discussed, have 7 valence electrons. And magnesium's going to be like, dude, do you want this electron? I don't want it. And the bromine is like, yes, I so wanted 1 more electron. So the magnesium reacts with a second atom of bromine. And now magnesium has a charge of positive 2 because it's lost 2 electrons. And it is surrounded or accompanied by 2 bromide ions that each have a charge of -1. All right. Now here's the thing. I remember Jen asked earlier, do we have to worry about the numbers for ionic compounds? Do we need to worry about like saying that there's 2 bromines in magnesium bromide? And the beautiful thing is you don't. And the reason why is magnesium will always have 2 valence electrons and bromine will always have 7. So bromine will always want to gain 1 valence electron. Magnesium will always have 2 to give. And so magnesium will always join up with 2 bromides. So that's why we don't have to include the numbers. Cool? All right. This is the official end of chapter 4. We're done with chapter 4. We'll start chapter 5 on Monday. Now, we definitely covered a lot of material here. So I highly encourage you to dig into this over the weekend. It's going to be a significant component of exam 1. And hey, let's hit up office hours. I'm gonna bounce right now, but we'll be back at 3. I'll be here from 3 to 6. So come back. We can work some problems. We can do some more examples. I can cook up some like really difficult ones and see how you guys handle them. Cool. All right. I'm gonna bounce rapidly, hurriedly, shove some food into my face, and I will be back in 30 minutes. Later, dudes.